Hello APC Mechanics students, today we'll solve the past paper FRQ 2012, exercise number 3. Then let me start. A ring of mass capital M and radius capital R and rotational inertia mr square is initially sliding on a frictionless surface at constant velocity v0 to the right as shown above. So if you notice carefully, the ring is sliding only, which means, okay, apart from that, we can talk about two variables of motions given by omega and v. This is related to rotation, this is related to translation. Since it is initially sliding, then it admits only initial speed and it has no angular speed until it reaches basically this moment in which we have friction. Remember that friction, it provides torque for the wheel and converts part of the translation motion into rotational motion. At time t is equal to 0, it encounters a surface with coefficient friction of mu and begins sliding and rotating. This is important. So because it's sliding and rotating, and it's apparent from here, so because it's sliding and rotating, there is no, okay, we have v and we have omega, but mathematically they are not related to each other. Whereas if you look here carefully, after it has covered the distance capital L, it will begin to rotate with no sliding. For sure there will be translational motion, but whenever we have rotating with no sliding, which means rolling without slipping, then v and omega are related mathematically via the following relation. Now in part A, what they're telling us is the following. Starting from Newton's second law in either translation or rotational form, as appropriate, derive a differential equation that can be used to solve for the magnitude of the following as the ring is sliding and rotating. So here we are in the regime where it's sliding and rotating. Mathematically they are not related. In part I, they're asking us to derive the differential equation for the linear velocity of the ring as a function of time. So because they have stated linear velocity, it means that we need to use Newton's second law for translation. Then let me state here, apply Newton's second law for translation. Which is given by F naught is equal to capital MA, and here let me state the following. Directly we can guess that the differential equation, because we have friction and the coefficient of friction is given by basically mu, the differential equation would be given by A is minus mu g, and we will explain later why this is a differential equation. Now let me proceed. Now what are the forces that are acting on the ring? We have the pull of gravity, the normal push, friction equals to MA. Now this is a vector equation that gives the birth to several linear equations, basically two. So let me say projection along the horizontal. And then along the horizontal, what do we have? That would be 0 plus 0. Now friction would be minus FF is equal to MA, and that would be minus mu Fn equals to MA, and between brackets we can write that the normal push in this case is balanced by the pull of gravity. Then minus mu mg equals to MA, m cancels with m, so A is equal to minus mu g. Now this is capital M. Now why this is a differential equation for the linear velocity? Because remember that A is related to V via calculus by dv by dt equals minus mu g, and indeed this is a differential equation. How do you know that it's a differential equation? Equation because we have an equality, and differential because it includes a derivative for the linear velocity. So basically that's what they're asking for. Alright, now in idea number 2 we need to repeat the same thing, but now for rotation. So let me say apply Newton's second law for rotation. and it's given by tau naught is equal to I alpha. And here let me state it carefully. Okay, first let me draw the ring here, then I'm gonna erase it. Now, in order to utilize this equation perfectly, we need to represent the forces. Now here in this case it's easy, but here let's represent the forces in a rigid body diagram. So the pull of gravity would be acting from the center like this. The normal push would be acting from the point of contact between the ring and the surface, and friction would be backward. It's not because it's moving to the right, but you should think about it because friction provides torque in order for the ring to rotate in the clockwise direction. So that's friction. Now that would be the torque of a gravity plus the torque of the normal push plus the torque provided by the friction is equal to I alpha. And here this equation cannot be resolved unless we understand what's our pivot point. In the case of rotation without slipping, you can consider two pivots, which is the center and this point. But here, because there is rotation with the slipping, which is rotating with the sliding, the only point that you can consider is this point. Now, why it is important for us to identify our point of rotation? Simply to identify what does I represent, because I from point to a point is different, as well as for the torques. Now, because we're considering the pivot to be this point, then I should be the rotational inertia of the ring around its center, which is given by mr square, which is the most inertial object, multiplied by alpha. And now what about the torque produced by gravity? The pull of gravity has a line of action passing through the center, so it produces no torque. Similarly for the normal push, so that would be 0 plus 0. Then the only force providing torque is the friction. That would be the radius, and it's being applied tangentially and in the positive direction that we're assuming, which is causing motion. Then that would be friction FF multiplied by R. Now we know that friction from this relation is given by mu Fn, and Fn is mg, so here we can write mu mgr, this is capital M. That would be equal to mr square multiplied by alpha. Now this would cancel with this, m cancels with m, and in this case we have mu g is equal to r multiplied by alpha. Then alpha is given by mu g divided by r. Now why this represents a differential equation for the angular velocity? Because we know that alpha and omega are related via calculus. Then d omega by dt is given by mu g divided by r. So basically that's the differential equation as function of time that we're searching for. Now they're telling us in part B, derive an expression for the magnitude of the following as the ring is sliding and rotating, the linear velocity v of the ring as function of time. So notice for the first glance you might think about that idea number 1 for part A and idea number 1 for part B, they are the same. But in the previous part they're asking for the differential equation. Here they're asking for the magnitude of the following as the ring is sliding down. So we need basically to find v as function of time. Now the moment we know that the acceleration is given by minus mu g, and which is constant, so we can basically use kinematics in order to solve for the linear velocity. Now we know that Vx is given by Vx0 plus Ax multiplied by t, knowing that the initial velocity is given by V0, so that would be V, that would be V0, and that would be minus mu g. Then in this case the magnitude for the velocity is given by V0 minus mu gt. Now why this is the magnitude set to be positive? Because the initial velocity, it's greater than this one. Okay, so this is already positive in value and it has still velocity in the positive direction. Now the angular velocity omega of the ring as function of time, we know that also because alpha is constant, we can use kinematics again, and we can say that omega is equal to omega 0 plus alpha t. Now remember that here initially we have only sliding, so omega 0, the moment it reaches this point, is given by 0, so that's 0, and alpha is given by mu g divided by r. Then in this case, omega is given by mu g divided by r multiplied by t. And indeed, this is the magnitude because everything is positive. And if you notice that they told us to express all our answers in terms of the following, so let's do a check. So here, indeed, okay. As well for these two, especially that V0 is an allowed quantity. Now moving on to part C, they're telling us derive an expression for the time it takes the ring to travel the distance L. The moment they mention the distance L in the exercise, it means that we need to use it. And if you think about it, if we need to solve for a time, we need to set up an equation in order to solve, in order to find the time. And the only way to do it, since we're talking about the distance L, at the end of the distance L reaching this point, we start having rotating with no sliding. So the only equation at our disposal that we can think of in order to solve, which is given by V, is equal to R omega, okay. So let me write here at the end of L. And the reason is that rotating with no sliding. Now we can use this equation and this equation, substitute them here and solve for t. Why this is allowed? Because remember, the equations that we have derived, they are applicable in this region, including the initial point and including the final point, because these are points of continuity of the problem. So now we can say that V0 minus mu gt is equal to mu g divided by r multiplied by t. So let me say here, this is r multiplied by mu g divided by r multiplied by t. Now r with r would cancel, then v0, and we're solving for t. Now what's the type of this equation? This is a linear equation that would be equal to mu gt plus mu gt, then which is given by v0 is equal to 2 mu gt. Then in this case, the time that we're searching for is given by V0 divided by 2 mu g. So what does this time represent? This time represent, or the duration for which the ring will roll from this initial point to this final point. So as you can notice that it only depends on it only depends on V0 and mu, okay? Now in part D, derive an expression for the magnitude of the velocity of the ring immediately after it has traveled the distance L. So this is straightforward. Now we know that the velocity as function of time is given by so, and we have time given by that, so we can simply replace this time and the function for the velocity and derive the expression. Now V is given by V0 minus mu gt. I repeat that this is only valid from 0 to L, including L. For this reason we can replace the time. So that would be V0 minus mu g multiplied by V0 divided by 2 mu g. Now mu g would cancel, and here we would have V0 minus V0 divided by 2, which is basically V0 over 2. Then at the end of the distance, the initial speed given by V0 is cut into half by V0 over 2, because there is a conversion from rotation to translation. Then V is given by V0 divided by 2. Now finally, the last part of this exercise, they're telling us to derive an expression for the distance L. Again, we can use kinematics. You can think about any equation, whether x is x0 plus v0t plus half axc square, or vx square is equal to vx0 square plus 2x delta x. All of them work. So then let me use vx square is equal to vx0 square plus 2ax delta x. And remember that all of these vector quantities, they might be positive or negative. Now delta x is the distance or displacement, which is L. Ax, it's important to note again that these are vector quantities. They should be replaced with a positive or minus sign. That would be minus mu g. The initial velocity is given by v0, and the final velocity is given by v0 divided by 2. Now we can do the replacement. That would be v0 divided by 2 to the power of 2, which is equal to v0 square minus 2 mu g L, and we're interested in determining L, so that would be v0 square divided by 4 is equal to V0 square and minus 2 mu GL. Now this can be written as 4 over 4, taking it to the other side, and 1 over 4 minus 4 over 4, that would be basically 3 over 4. Then 3 over 4 V0 square is equal to minus 2 mu G multiplied by L. Now minus with minus cancel. 2 multiplied by 4, that would be 8, dividing by mu G. Then L is given by V0 square multiplied by 3 divided by 8 mu G. Alright? And that's it for me in this video, guys. See you soon in a new one.